Do the fundamental rules that govern our universe ever change? I mean, can things like the strength of gravity actually vary over time?
That is, well, it's one of the biggest questions, really. If these constants we, rely on turn out not to be constant,
It changes everything.
it really shakes the foundations of physics, yeah.
Okay, let's dive into this then. Today, we're exploring exactly that question. Could the fundamental constants, specifically the gravitational constant g, actually vary over cosmic time?
Mm-hmm. And we're looking at what the latest research suggests, including, some really fascinating insights from missions like Gaia.
So our mission today is to unpack what a fundamental constant even is, why we're testing if they're constant in the first place.
Right, and how we actually try to measure if G gravity's strength is changing, and crucially, where this new astronomical data fits in.
Perfect. So let's start right there. What exactly is a fundamental physical constant?
Okay, so think of them as the universe's settings, almost. They're numbers that we believe are universal, the same everywhere, and constant in time.
So they shouldn't change.
That's the standard assumption. And they can also be dimensionless, just pure numbers, like the fine structure constant for electromagnetism.
And how many are there? I remember reading it depends on the theory you're using.
That's exactly right. If you take our current best theories, that's general relativity for gravity and the standard model for particles and the other forces.
And electromagnetic, strong, and weak nuclear forces.
Correct. Combining those, you end up needing 19 fundamental constants, 19 numbers that the theories themselves don't predict.
We just have to measure them, find out what they are experimentally.
We have to measure them, yep. Which, is kind of a hint that maybe our understanding isn't quite complete.
Because we're still missing big pieces, right? Like a theory of quantum gravity or what dark matter and dark energy actually are.
Precisely. So it's quite natural to ask, could these constants actually be changing, evolving, maybe pointing towards that deeper theory?
And that's why testing them is so critical, finding out if they change, or even putting a limit on how much they could possibly change.
It's a direct test of our fundamental theories, a discovery that G, or any other constant, varies would be. Well, revolutionary doesn't even cover it.
Okay. Now, before we zero in on G, you mentioned there are ways to test other constants.
Yeah, absolutely. Scientists have developed some really clever methods over the years. Usually, for testing those other constants, you assume G is constant, just as a baseline.
Makes sense. So what kinds of methods are we talking about? You can do lab experiments today, obviously.
Super precise lab measurements, looking at atomic transitions, things like that. But we can also look back in time. Well, there's the Oklo natural nuclear reactor in Africa. That was active almost 2 billion years ago.
Wow, a natural reactor.
Yeah. It gives us a snapshot of nuclear physics way back then. We can also look at isotopes in really old meteorites. Their decay rates tell us about physics from billions of years ago.
And looking even further out, distant objects.
Exactly. Analyzing light from quasars, which are incredibly distant and bright, lets us probe things like the fine structure constant when the universe was much, much younger.
You can also look at how stars make elements, like carbon.
Stellar nucleosynthesis. Or even go right back to the early universe, the cosmic microwave background radiation, the amount of hydrogen and helium formed just after the Big Bang. All of these give clues.
So a whole toolkit of methods. But I guess interpreting them isn't always straightforward.
No, definitely not. Each method has its own, complications and assumptions you need to make, but together they give us a pretty good picture for the non-gravitational constants.
Okay, so let's bring it back to gravity. The gravitational constant, G.
Mm-hmm.
What does our best theory of gravity, general relativity, say?
Well, GR, based on something called the equivalence principle, strongly predicts that G is constant. It's built into the theory's structure.
But measuring its actual value? That's hard.
It's surprisingly difficult. Compared to, say, the speed of light, measuring G precisely is a real challenge. The latest official value from CODATA in 2018 is about 6.674 times 10 to the minus 11 in standard units.
And the uncertainty.
That's the key thing. The relative uncertainty is about 22 parts per million, which sounds tiny, but for a fundamental constant, it's actually quite large.
Much larger than for other constants.
Oh, yeah. And that inherent fuzziness in its current value makes it really tough to nail down whether it's changing very, very slowly over time. You're looking for a tiny change in a number we don't know perfectly to begin with.
And people have wondered about G changing for a long time, haven't they?
Oh, yes. Decades. People like Weil, Eddington, Dirac, They speculated about it, often connected to something called the large numbers hypothesis.
What was that?
It was noticing some, well, frankly, weird coincidences between really huge numbers in physics, like the ratio of the electric force to the gravitational force between electrons, or the age of the universe measured in atomic units. They're vastly different scales, yet some ratios seemed related.
Which made people wonder if the constants involved were somehow linked and maybe changing together as the universe expands.
Exactly. That was the idea. It's mostly fallen out of favor, but the underlying question, could G vary, remains very active.
Okay, so how do scientists try to measure if G is changing now? What are the actual experiments?
Broadly speaking, there are three main classes of experiments or observations used to put limits on A, that's G dot, the rate of change of G over time.
Right. What's the first class?
Solar system observations, basically tracking things really precisely within our own cosmic backyard.
Like the moon's orbit?
Yep, lunar laser arranging bouncing lasers off reflectors left on the moon. Also using radar timing to Venus and Mercury, measuring the round-trip travel time very accurately, and analyzing data from spacecraft like Mariner 10 back in the 70s and the Viking landers on Mars.
How does tracking Viking help?
Well, by precisely measuring the distance between Earth and the landers on Mars over time, you can test if the gravitational pull between the Sun, Earth, and Mars is exactly as predicted by GR with a constant G.
I see. And did that give a limit?
It did. The Viking data gave a limit on AGI of around a few parts in 10 to the 11 per year, but its precision was actually limited by something else.
What was that?
How well we knew the masses of all the asteroids, the minor planets buzzing around the solar system. Their gravity subtly affects the orbits, too.
Ah, okay. So that's the solar system. What's method number 2?
Pulsar timing. This involves monitoring pulsars, which are incredibly dense, rapidly spinning neutron stars. They emit beams of radiation like lighthouses.
And they are incredibly stable clocks, right? Some of them.
Astonishingly stable, especially those in binary systems, two neutron stars orbiting each other. The most famous is probably PSR B1913 plus 16, the first binary pulsar discovered.
Hulse-Taylor pulsar won a Nobel Prize.
That's the one. Now, general relativity predicts that such a system should lose energy by emitting gravitational waves, causing the orbit to shrink or decay at a very specific rate.
So you measure the orbital period getting shorter.
Exactly. You time the arrival of the pulses over years, even decades, and you can measure that orbital decay very precisely. If G were changing over time, it would add an extra contribution to that decay rate on top of the gravitational wave emission.
So you look for any deviation from the GR prediction.
Precisely.
Yeah.
And the limits from systems like B1913 plus 16 are very good, comparable to the solar system ones. But again, there's a catch, limiting the precision.
Not asteroids this time.
No, this time it's more about our lack of perfect knowledge of the pulsar system itself within the galaxy. Things like the sun's exact distance from the center of the Milky Way, and the pulsar's own motion through space, its proper motion, and its exact distance from us. These galactic uncertainties are actually the biggest source of error in the G constraint from pulsars right now.
Interesting. Okay, solar system pulsars. What's the third approach?
Using stars themselves as laboratories, constraints from stellar evolution.
Ah, okay. Now we're getting closer to where Gaia might come in. How do stars tell us about G changing?
The basic idea goes way back to physicists like Teller and Gamow. A star's fundamental properties, especially its luminosity, how bright it shines, and its lifetime, are incredibly sensitive to the value of G.
Ah, sensitive.
Well, a very simplified model suggests a star's luminosity scale is something like G raised to the power of 4.
G to the 4th. Wow, that's a huge dependence.
It really is. It means even a tiny change in G over a star's lifetime would have a really dramatic effect on how quickly it burns through its nuclear fuel.
Like that example you mentioned earlier.
Right. The source mentions that under one early idea from Dirac about how G might vary, our own sun should have burned out billions of years ago. The fact that it's still shining puts a strong constraint right there.
Okay, so that's a basic check. But scientists use more detailed models.
Oh, yes. Much more sophisticated stellar evolution models, particularly for understanding populations of stars, like those in old globular clusters. These are tightly packed groups of stars, all born around the same time.
And you look at how those stars have evolved.
Exactly. You look at something called the main sequence turnoff. That's the point on a diagram of star brightness versus color, where the most massive stars still burning hydrogen are just starting to run out of fuel and evolve into giants. The position of that turnoff point tells you the age of the cluster.
And that age depends on G.
Yes, because G affects how fast the stars burned their fuel. So, by fitting the observed turn-off age to the models, assuming G might have changed linearly over time, you can constrain how much it could have changed.
What kind of limits does that give?
The source mentions limits around, say, a few parts in 10 to the 12 per year. Interestingly, some studies found the limits allowed for the possibility that gravity might have been slightly weaker in the past.
Huh. And we can also study our own star, the sun.
Yes, using helioseismology. That's the study of the sun's vibrations, its sunquakes. These vibrations, or modes, depend very sensitively on the sun's internal structure.
Like using earthquakes to study Earth's interior.
Exactly the same principle. By comparing the observed frequencies of these solar oscillations to those predicted by models of the sun's evolution, you can get very tight constraints on G's variation. In fact, the source indicates the most stringent limit from stellar evolution comes from helioseismology constraining G to be less than about 2 by 10^13 per year.
That's incredibly small. So stellar evolution generally is powerful, but the source puts a special focus on white dwarfs. Why are they so important for this?
Because they're ancient. White dwarfs are the end-stage remnants of stars like our sun. They've basically run out of fuel and are just cooling down over billions and billions of years. If G has been changing, you'd expect the cumulative effect to be largest in the oldest objects we can find.
And white dwarfs are among the oldest things in the galaxy.
Precisely. They are cosmic fossils.
Okay. And the research highlights two main ways white dwarfs are used to probe G. What's the first one?
The white dwarf luminosity function. This is basically a census counting how many white dwarfs there are at different levels of brightness or luminosity.
So you just count the white dwarfs.
Sort of. The key is that the faintest white dwarfs are the oldest ones. They've had the most time to cool down. Their evolution is dominated by this slow cooling process, plus some gravitational contraction.
And G affects the cooling.
Yes, because a change in G modifies their internal structure, their energy balance, and therefore how quickly they radiate heat and cool down.
So the rate of the white dwarf thermometer depends on G.
That's a good way to put it. Now, if you look at the distribution of white dwarf brightnesses, you find a sharp drop-off at the faint end. That drop-off represents the oldest white dwarfs in, say, the galactic disk. They haven't had time to cool beyond that point yet.
So the position of that drop-off tells you the age of the disk.
Exactly. And that age estimate depends critically on the cooling rate, which, as we said, depends on G throughout the past. So by comparing the observed luminosity function drop-off with theoretical cooling models that allow for a varying G, you can set limits on A.
Have people done this?
Yes, earlier studies mentioned in the source use this method to get limits on AG around 1011 or 1012 per year. And the expectation is that with better data on the luminosity function.
Which Gaia should provide.
Exactly. Gaia's ability to measure distances and brightnesses for huge numbers of white dwarfs should allow for a much more precise determination of the luminosity function, leading to tighter constraints on G variation.
Okay, that's the luminosity function. What's the second white dwarf method?
Looking at individual pulsating white dwarfs. Some white dwarfs actually pulsate, getting slightly brighter and dimmer with very regular periods.
Like tiny cosmic heartbeats.
Kind of. There are different types, but the key thing is that their pulsation periods are incredibly stable over long timescales.
But if G changes?
If G changes over time, it would slowly alter the white dwarf's internal structure, its size, density profile, and also its overall evolutionary timescale. Both effects would cause the pulsation periods to change gradually.
A tiny drift in the period over years.
Exactly. We're talking incredibly small changes, like fractions of a second accumulating over decades.
And are there specific stars being watched for this?
Oh, yes. The source highlights a couple, like R548, which has been monitored since the 1970s, and especially G117b15a. That one's been watched since 1974, and is sometimes called the most stable optical clock known in the universe. Its main pulsation period is incredibly regular.
Monitoring a star's pulse for 50 years.
Yet,
That takes dedication.
yeah,
And this gives good limits.
it does. By measuring the rate of change of the period, denoted pi dot, scientists have derived limits on AGI on the order of 10 per year from these stars. But there's a very important subtlety here.
Okay, what's the catch this time?
You have to account for the star's motion across the sky, its proper motion.
Why does the star moving sideways affect its pulse timing arriving here?
It's a kinematic effect, often called the Shklovsky effect. Think of it like this. As the star moves across our line of sight even slightly, there's a tiny, apparent Doppler-like shift in the timing of the pulses arriving at Earth, purely due to its changing velocity relative to us. It mimics a real change in the star's period.
So the observed change in period isn't necessarily the true change happening inside the star.
Correct. The observed U is a combination of the true intrinsic period change, which is what we need for the G constraint, and this apparent change caused by the star's transverse motion. You need to calculate and subtract that motion effect.
And to subtract it accurately, you need to know the star's motion and distance very precisely.
Exactly. And this is where Gaia has made its most direct contribution so far, according to the source material.
Okay. Finally connecting the dots to Gaia directly.
Yes. Gaia provides extraordinarily precise measurements of stellar parallax, which gives distance, and proper motion, the movement across the sky.
So for a star like G117b15, Gaia tells us how fast it's moving sideways and how far away it is.
With incredible accuracy, the source gives the numbers. Gaia DR2 measured G117b15a's parallax, implying a distance of about 187 light-years, and measured its proper motion very precisely.
And using those Gaia numbers.
Using those Gaia measurements, astronomers could calculate the apparent period change due to motion much more accurately than before, subtract it from the observed period change, and get a much cleaner measurement of the intrinsic period change. That intrinsic change is what's used to set the limit on the variation of G.
So let's be clear then. Based only on this source, Gaia hasn't single-handedly produced a brand new, dramatically tighter limit on G variation yet.
That seems to be the case. Its main contribution highlighted so far is providing the crucial, high-precision astrometric data, the proper motion and parallax needed to refine the calculations for existing methods, specifically the pulsating white dwarf technique for stars like G117b15a.
But the potential for the future is huge.
Absolutely. The source is quite clear that Gaia is expected to make significant further contributions as more of its data releases are analyzed and incorporated into these studies.
Okay, so where else are we expecting Gaia to help tighten the screws on G?
Well, first, as we mentioned, by providing that vastly improved white dwarf luminosity function, that should lead to much more stringent limits from the population statistics method.
More precise ages for the galactic disk.
Right. Second, Gaia will provide accurate proper motions and distances for many more pulsating white dwarfs, not just the few very bright, well-studied ones like G117b15a. A larger sample size will improve the statistical power of the period change method.
And it helps with the pulsars too, right? You mentioned the galactic constants and pulsar distances were limiting factors there.
Exactly. Gaia's mapping of the Milky Way and its precise measurements of star positions and motions, potentially including some pulsars or their companions, will help nail down those galactic parameters in pulsar astrometry. That, in turn, should significantly reduce the uncertainties in the limits derived from binary pulsar timing.
It even mentions Gaia helping with the old Viking lander constraints.
Yeah, potentially. By improving our knowledge of the masses and orbits of those pesky minor planets, the asteroids, which were a limiting factor for the Viking ranging precision, Gaia observes asteroids too.
And looking beyond the Milky Way.
There's potential there too. The source suggests Gaia's precise measurements of stars in nearby galaxies, like the Large Magellanic Cloud, especially variable stars like Cepheids in eclipsing binary systems, could eventually help test gravity in different environments.
Wow. It's really remarkable how one mission, designed primarily to map our galaxy, ends up having such deep implications for testing fundamental physics.
It truly is. It shows how interconnected these different areas of astronomy and physics are. And, there's another layer to these white dwarf studies the source touches on.
Oh, what's that?
These same ultra-precise measurements of white dwarf pulsation periods aren't just sensitive to gravity changing. They can also be used to search for or place limits on other kinds of exotic physics.
Like what?
Well, things like hypothetical particles called axions, which are a dark matter candidate. If axions exist and interact weakly with electrons or photons, they could provide an additional cooling mechanism for white dwarfs, which would affect their pulsation periods.
So the white dwarf pulsations act like detectors for new particles too.
Potentially, yes. By measuring the period change very accurately and comparing it to the standard cooling models, you can constrain how much extra cooling could be happening due to things like axions, or perhaps even certain properties of neutrinos.
So these pulsating white dwarfs are like Swiss Army knives for fundamental physics.
That's a great way to think about it. They probe gravity, stellar evolution, and potentially physics beyond the standard model, all through these tiny regular pulses.
Okay, let's try and sum up this deep dive. It seems the quest to find out if fundamental constants like gravity strength G are truly constant is Well, it's incredibly difficult.
It's painstaking, long-term work, absolutely. But it's so fundamental. It tests the very bedrock of our understanding of the universe.
And progress comes from multiple angles using the solar system. Distant pulsars, the evolution of stars, the cooling of white dwarfs.
Mm,
It's not just one magic bullet experiment.
exactly. Multiple independent lines of evidence are crucial. And what's clear is that high-precision astronomical data, especially for missions like Gaia, is becoming absolutely essential for pushing those limits further.
Gaia's data is feeding into many of these different methods, refining the calculations, reducing uncertainties, especially for methods relying on old stars like white dwarfs.
It's providing the incredibly accurate measurements of distances, motions, and brightnesses needed to make sense of these subtle effects we're looking for.
It really is a massive ongoing effort at the frontiers of measurement.
It is, and it leaves you with a pretty profound thought to chew on.
Which is,
What if they do find something? What would it actually mean for our picture of the cosmos if we discovered definitively that gravity hasn't been the same strength throughout history, that it's been getting weaker, perhaps, or stronger?
how would that single discovery ripple through everything else? Cosmology, particle physics, our understanding of stars, galaxies, the fate of the universe.
Exactly. It would force a fundamental rewrite of physics. And that possibility, however remote, is what keeps scientists pushing these measurements to ever greater precision.